exercise so that you can actually see how we derive at different kinds of results. But I would like to start off this class by discussing, or in fact reiterating, something that we've already seen. Now if you look here, this is a list of most of the 4F group ions. All of them are trivalent. This is the electronic configuration. We apply Hund's rules. Hund's rules are a manifestation of the exchange interaction and the spin-orbit interaction. The first two rules come out of exchange interaction between the electrons. That is, S is maximized, then you have to maximize L in conformance with the first rule, and the third rule is a manifestation of the spin-orbit interaction in which L and S couple together to give you an overall J. And depending upon whether the shell is less than or more than half filled, you get J equals L minus S or L plus S. So using these Hund's rules, one can find S, L, J, and one can also find the term symbols corresponding to these ions. Now the value of J represents whether that particular spin is magnetic or not. You place it inside a magnetic field, each J will split up into 2J plus 1 levels. This is a paramagnetic ion with this corresponding value of J. It is described by a Brillouin function. It has a certain field and temperature dependence. You can get a susceptibility. So all of these are paramagnetic ions. Now this is the value of P, the effective magnetic moment calculated from these values of L and J. You can calculate the lambda J factor, then you can put it inside the value for the effective magnetic moment, which depends upon the Bohr magneton, the value of J and Gj, and these are experimentally determined magnetic moments in units of the Bohr magneton. So notice that there is a finite number of electrons, so one electron, but the magnetic moment is not one Bohr magneton. These are fractional numbers, these are not integers, and they have nothing to do with the number of electrons inside the shell. These come out because of the fact that there are different S, L and J values, and you have to insert these values into the proper formula to get the effective number of Bohr magnetons for that particular ion. You will see really good correspondence between the experimental and theoretical values, okay, with a few exceptions. This particular ion, paraceodimium, probably its magnetic moment is not available. There's a discrepancy here for europium because all of these terms assume the ground state. These are the ground state terms, but there are also excited states, and if the excited states are present close to the ground state, there could be intermixing between the ground and exciting state. So probably this is the reason why this experimental value does not match the theoretical value. For all other ions, there is really good correspondence between the experimental and the theoretical value. So all is well and good for the 4F ions, the rare earths. However, if we come to the 3D ions, we apply the Hund's rules once again, we find the term symbols. This is the theoretical effective magnetic moment that comes out. Okay? So the effective magnetic moment, you might all recall, is given by, so mu F over mu B is what we've defined as P here, and this is Gj J plus 1 okay. So this value is plotted for all of these ions. This is the value of P. Now you will observe that the experimentally determined magnetic moments, which come out from experimentally determined susceptibilities, is vividly different from the theoretical values. So 1.55, 1.70, they're not similar. However, if I assume L to be equal to 0, if L equals 0, then J must equal S. So if instead of these values of J, I put in the value of S over here, and for S we know that the Lagrange factor is 2. If I use these values, instead of using the orbital angular momentum, I use just the spin and I predict what the effective magnetic moment is, then these moments are in fact good agreement with the experimental values. So something is wrong here. Something is clearly outside the scope of what we've been discussing so far. If you had a gas of these ions, for example, you had a gas of manganese fluoride, then in a gas, each molecule is separate from the other, which means you have free ions. Then the experimental values are in good agreement with these values. However, once you place these ions inside a solid matrix, inside a crystal, the values change, they depart, which means that the environment also has some influence on the ion. And this is something that we're going to study today. It's an important interaction when we start studying paramagnetic ions embedded inside a solid matrix, inside a crystal. So we're going to look at the crystal field effects and the crystal field interaction, which is an extremely important interaction. So this was the motivation. Now for the 4F ions, we know that there is a spin-orbit interaction and there is exchange interaction, and this results in atomic states which are defined by J, the total spin quantum number, its azimuthal component L and S, which means that each ion has a specific value of J, L and S, and these are good quantum numbers. Okay, J is determined by the spin-orbit interaction, L and S are determined by the exchange interaction and the interaction between the electrons. So the 4F ions have good values of J, L and S. These are, in other words, eigenstates of the overall Hamiltonian. However, in the 3D orbitals, the situation is totally different. We've seen that L and S are no longer good quantum numbers. So how do we describe this effect? If you look at this curve over here, this one, over there, so they need to remember this. If you look at this curve, if you look at the 4F orbitals, this is 4F orbital, and this is closer to the nucleus as compared to 4S, 4P and 4D. So it's closer, the 4F is closer to the nucleus. The valence shell is actually closer to the nucleus. 4S, 4P and 4D orbitals are further away from the nucleus. So the 4F orbital, which houses the valence electrons, is shielded from the environment because it's closer to the nucleus. This curve is a curve of the radial probability density of different orbitals. However, compare this with 3D. This is 3D. This is the probability density for 3D. This is 3P and this is 3S. 3D as compared to 3P and 3S, there is an appreciable fraction of this probability density which overlaps with 3s and 3p, and it is not as good, it's not as well shielded from the environment as the 4f orbital. In other words, the 3d orbital extends to regions further away from the nucleus. So it has a greater propensity of being affected by the environment. Now the question is, how does the environment affect the 3D orbital? For that, what we need to see is a model. This kind of interaction in which the orbitals are interacting with the field of the crystal is called the crystal field interaction. Okay. Now we know that if I have an ion, say a metal ion, which is a cation, positively charged, and this is in the vicinity of anions, negatively charged ions, for example oxygen. Okay, so this is an oxygen anion, another oxygen anion. These are negatively charged centers, each carrying a charge of 2 electrons. Now whatever the orbitals of this metal cation are, for example, if I consider the pz orbital, and if I draw the probability density for the pz orbital, then this negatively charged cloud is in the vicinity of another negatively charged anion, and there is an interaction, which means that this interaction will change the energy of this orbital as compared to another orbital. So if I draw the px orbital, suppose this is the px orbital, the energy of this orbital might or be different. It might or might not be different. So different orbitals interact with neighboring ions in different manners. These neighboring ions are generally called ligands. And these ligands are disposed around the central paramagnetic ion in different ways. So the ion is encapsulated in different kinds of cages of the ligands. This means that the crystal structure itself will have an effect on the energy levels. And different kinds of orbitals will interact with differently. And if I would like to write down the Hamiltonian for this interaction, this Hamiltonian corresponds to a certain energy. So what this Hamiltonian will be, this Hamiltonian will be given by the interaction of the charge density of the metal electrons with the potential that the electron sees. And that potential is created by the ligands. So this is going to be rho into some potential at that particular location, which is created by the ligands. So in this manner, one can find out the energies of the different orbitals. Now in all the d orbitals, if in a free ion, are at the same energy. So there are 5 kinds of d orbitals. We all know that. All of them have the same energy. They are degenerate. Those d orbitals are labeled as dz square, dx square minus y square, dxy, dxz, and dyz. All of these 5 orbitals have the same energy. They are degenerate. However, once this ion, in which there could be some electrons in these d orbitals, okay, there are some electrons in these d orbitals. Now when this ion is placed inside an environment, the energies of the different orbitals might change, and the degeneracy might in fact be lifted. And the lifting of the degeneracy is encapsulated by the Hamiltonian. These electrons see a new Hamiltonian, which is the crystal field Hamiltonian. So this acts now as a perturbation on these orbitals, and we have to find out the corrections to the energy due to the crystal field Hamiltonian. For that purpose, we need to find out what the eigenstates of this Hamiltonian are. Since all of these are degenerate, we have to use degenerate perturbation theory. So it's important to find out the eigenstates of the crystal field Hamiltonian. It turns out that these 5 orbitals that I've written over here are eigenstates of this Hamiltonian. Now it's important to realize what these orbitals actually look like. So it's nice to draw diagrams, and I'll show you how to draw these diagrams on the computer as well. If I define these to be my axes, x-axis, the y-axis and the z-axis, then the dz orbital looks something like this. Okay, this is the probability. I'm drawing here the probability density. Okay, this is the dz square orbital. Likewise, I have the dxy orbital. The dxy orbital has the lobes on the x and the y axis. Okay, so this is dxy. Likewise, I have three other orbitals. Now what I'm trying to do, I'm making this the x-axis and this the y-axis, so I can easily draw the remainder of the 3 orbitals, and I'm looking at this configuration from the top. So the dxy orbital has its lobes in between the axes. Okay, so this is dxy. Likewise, I can have dxz. dxz has this, is dx square minus y square. This is dxz, this is dxy, and I have the 5th one, which is dyz. So this is the y-axis, this is the z-axis. So there are 5 different kinds of orbitals. Okay? And where do these orbitals, where do these shapes come from? These are nothing but spherical harmonic functions. If you look at these documents that I've given you here, I'm going to go slow today because I'm going to do quite a few calculations. So if you look at this document, which I'm pulling off on the screen here, so if you look here, the d orbitals correspond to the spherical harmonic functions in which L is equal to 2. So this, and this. These correspond to d orbitals. Okay, so this has L equals 2 and m equals plus minus 2. L equals 2, m equals plus minus 1. L equals 2, m equals 0. So you will notice that these have complex terms. These particular orbitals have complex terms. Okay, so what you need to do, but these terms over here, they are not complex, these are real orbitals. And these are eigen functions of the crystal field Hamiltonian, not these orbitals. So you have to create superpositions of these orbitals to create these orbitals. Okay, so let me explain that now. So if you look at the screen over there, d z square, which corresponds to the spherical harmonic function in which L equals to and L equals 0. function of theta and phi. This term over here, this thing, is given by 5 over 16 pi 3 cosine square minus 1. Now this is real, this is fine. Okay? And if I plot this function, this is what I get. Okay? Remember that if you equate this equal to 0, then this corresponds to a certain angle theta, and that theta is this angle. It's called the magic angle. It's about 54.74 degrees. Okay? So this is the dz square orbital. Now if I would like to, you will notice that if I take y2 plus 2 theta and phi, and I add to this y2 minus 2 theta and phi, and for normalization, if I divide this by under root 2, okay, on its own y2 plus 2 corresponds to this thing over here, and it has a complex number. Now if I take y equals with two terms with opposite values of m, that is m2 and m minus 2, and I add them together, I'm going to add these terms, one with plus and one with minus. So what I'm going to do is that I'm going to get 15 over 32 pi under root sine square theta e I2 phi plus e minus I2 phi, which gives me 1/2 of cosine of 2 theta. If I add the positive e I2 theta plus e minus I2 theta, that's equal to 2 times cosine 2 theta, and I also have this under root 2 here. So now this is a superposition of two orbitals. Okay? This orbital on its own was an eigenstate of the atomic Hamiltonian. You solve the Schrödinger equation, you get this orbital as a solution. But now if you would like to find the eigenstate of the crystal field Hamiltonian, you can test that this alone will not be an eigenstate. So you need to create a superposition of two states, of two wave functions or two spherical harmonics, which generates an eigenstate of the crystal field Hamiltonian, and the appropriate eigenstate is this one. Okay? So this is what is called dx square minus y square, and this is plotted over here. Notice that this is maximum when theta equals 90 degrees. That's why it's in the equatorial plane. And this is maximum when theta equals 0 or 90 degrees. Sorry, 5. When phi equals 0 or 90 degrees. You're taking the square of this because you're plotting probability densities. Okay? So now we have found out these two particular orbitals. Likewise, we can find out those orbitals over there. Okay? D, if I take, and what are those orbitals? Those orbitals, I have calculated these orbitals. If I take the difference of these orbitals, I will get another eigenstate. But then I would like to make this real. So eventually I multiply this with minus iota as well. This will make this function real. Because if I take the difference, I get iota sine 2 phi here. So I want to make this real, so I multiply this with minus iota. And I get something, okay? I get something. I don't want to calculate this. This I can do easily in some software. So this is another eigenstate. This corresponds to something, to either one of these. Okay? Since I have sine squared theta, sine of 2 phi. So it corresponds to dxy. Okay? When phi is 45 degrees, this is maximized. So this is dxy. Likewise, my dxz and my dyz will be given by superpositions of 2 plus 1 theta phi plus minus by 2 minus I theta phi over under root 2, okay, with the appropriate factor. So with the plus sign I have plus iota, okay. Again, with the plus sign I multiply this with plus iota to make this real, and if I have negative sign I multiply this with just 1, okay. So I can generate the other orbitals. Likewise, I can generate all 5 orbitals, and in the absence of a crystal field, all of these orbitals are the same. But these are just the spherical harmonic part, these are just the angular part, they depend upon theta and phi. Each one of them depends upon theta and phi. But the orbital actually has a radial part as well. And since we're talking about a 3D orbital, I have to multiply each one of these by the corresponding radial part, in which n equals 3, L equals 2. So I multiply each one of these with the corresponding R to obtain the overall orbital, right? Because the orbital has a radial part as well. So this is the complete orbital. What we've drawn here are just the angular parts. It's really difficult to draw the radial part along with this. And where are the radial parts? The radial parts are also given in the same sheet. So if you look here, I need to insert this value of R to generate the radial part. Okay, so each one of these is multiplied with the corresponding radial part of the wave function, which has n equals 3 and L equals 2. Now we have defined the orbitals. These orbitals are superpositions of eigenstates of the atomic Hamiltonian, and all 5 of these are eigenstates now of the crystal field Hamiltonian. And you can test this. You can always test this. Okay? You must test this. Whether these are really eigenstates of the crystal field Hamiltonian. Yes, they are. You can test this. Now what we would like to do, if the ion with these particular orbitals is placed inside a crystal, are the energies of these 5 orbitals the same or different? How are the energies split up? How is the degeneracy lifted? So that's what we're going to do now. Okay, and we're going to perform a calculation. A laborious, lengthy calculation, but I'll do it on a computer so things will be easy. But I would like to show you the flow of argument here. Okay. Now this 3D ion is embedded inside a host solid, and this is what magnetism is really all about. You talk about solids, not gases. Magnetism in gases just forms an iota of the whole field of magnetism. So you need to put things inside solids. Okay. The original motivation for work of this kind was when people started making lasers. If you remember, the Ruby laser, which was the one of the first lasers made in 1960 by Theodore Mammon, was a chromium ion, a chromium 3 ion, which is a 3D ion inside a matrix of aluminium oxide, sapphire. This is ruby. The optical transitions in ruby in chromium give you the red color. Right? You have erbium doped, which is a rare earth ion, fiber lasers. So the original motivation for studying these paramagnetic ions was indeed in the realm of optics and laser technology. Neodymium YAG, in which you have a neodymium ion, which is a rare earth, placed inside yttrium aluminum garnet, is another example. Now what we would like to do, we would like to find out their energies of these orbitals. But first of all, we need to pick up an environment. G.
This is sorry to cut you off. So I just wanted to clarify that we are studying the 3D orbitals because they are at the outermost, if you can say in terms of...
Not really outermost, but the reach is further away from the nucleus. There is a greater propensity that they will be influenced by the crystal field.
Okay, but in the case of the 4F, it is being shielded by 4S.
Very well shielded. So the 4F, for the 4F ions, the Hund's rules are satisfied. The exchange and spin orbit interaction is stronger than the crystal field interaction. So we have two regimes. If the spin orbit interaction is stronger than the crystal field interaction, then what we've learned so far is fine. And the Hund's rules work. So the Hund's rules work mostly, okay? Remember, the Hund's rules are also semi-empirical in nature. They have a motivation, but these rules are semi-empirical. So this is true for 4F. For 3D, the crystal field Hamiltonian is stronger than the spin orbit or the exchange interactions, which are determined by the interaction between the electrons. So the influence of the environment is larger. So that dominates and steers what kind of orbitals are formed. Okay? So this is true for 3D and other transition metals. Now let's pick up an environment. So there are different kinds of environments. One of the most popular environments is an octahedral environment. In an octahedral environment, as the name suggests, there is a central metal ion and it's coordinated by 6 ligands, negatively charged. And the assumption is that each one of these ions, these anions, is a point charge. This assumption breaks down in certain cases, but for simplicity, let's assume that the 6 are anions, each carrying a charge Q, which is negative, is a point charge. This is my x-axis, this is my y-axis, this is my z-axis. Alright. Now this is the octahedral environment. Now in the octahedral environment, the distance of this ion from each anion could be the same or different. If it's the same, we call this that it's an octahedral environment with cubic symmetry. Okay, if each one of these distances is the same, let's call this distance d. Okay. It's an octahedral environment which tells you the coordination and its cubic symmetry because each one of these distances is the same. It could be tetragonal in which one of the distances is different. It could also be orthorhombic in which all 3 kinds of distances are different. But let's assume that it's cubic symmetry octahedral environment. Another important environment is the tetrahedral environment. If I would like to draw the tetrahedral environment, I will draw a cube. The metal ion, the 3D ion, is at the body center of the cube, and this is coordinated by 4 anions on the diametrically opposite diagonals of the 2 edges. This is called the tetrahedral environment. Okay? So this forms actually tetrahedron, that's why it's called a tetrahedron. You can look at pretty visualization of this on the internet. This is the tetrahedral environment. And if each one of these distances is the same, it's called a tetrahedral environment with cubic symmetry. In terms of group theory or in crystallography, this kind of arrangement is denoted by OH, and this is denoted by TD. Okay. Okay. Now let's focus on the octahedral environment, and suppose that I have a 3D 1 ion, which means 1 electron, and a d orbital with just 1 electron, placed inside an octahedral environment with cubic symmetry. Now I need to find out the crystal field Hamiltonian. Okay, which means I need to find out the wave function of the d orbitals, which are written over here, and I need to find out the potential. So if I would like to find out the potential, the crystal field potential is a function of x, y and z. I'm sure this is something that you will immediately recognize. Now each one of these anions is being treated as a point charge. So this equals, each one of them has a charge q over 4 pi epsilon naught, and the distance of each one of them. Okay? So 1 over x minus d whole square plus y square plus z square due to one of these charges plus all other terms. There are 5 more terms. Okay, one along the x axis. One this sign and the other is this sign. Their coordinates are plus d and minus d. Plus 4 more terms. Now I'm going to write these 4 terms together for compactness. 1 over x square plus y plus minus d whole square plus z square. Plus x square plus y square plus z plus minus d whole square and root. So this is the crystal field Hamiltonian. Now I need to find out the energies of the orbitals, right? It's just, so I'm finding the potential at some point x, y, z, and the d orbital, whatever d orbital we're talking about, is extending in space. So I would like to find out the potential at this point, multiply with the charge density at this point, which comes out from the wave function, and integrate over entire space. This is how the potential varies with space. And I know how the orbitals give you a different probability densities. So now I know how to construct the Hamiltonian. Now what I need to do is that I need to find out the energies. Now it appears that these orbitals are eigenstates of the Hamiltonian. So energies, which are the perturbations in energy, are simply found out by terms of this kind. Now for simplicity, since I want to use the computer, I would like to relabel these states. I call this D1, all of this, I call it D1 for simplicity, because I would like to put a symbol in the computer. I call it D1, D2, D3, and D4 and 5. So D4 and 5 is this entire state over here. So what I need to do, I need to calculate HCF di di. Since these are eigenstates, if this is dj and j is not the same as I, then this turns out to be 0. So I need to calculate terms of this kind. I have the crystal field Hamiltonian. Okay. Now the crystal field Hamiltonian this is just a perturbation. So I need to find out, I need to expand this term and put it in here. And I put the orbitals or the wave functions from what I've written over there. Now I'm going to do all of this on my computer in front of you. Okay? So that we can follow the chain of how to do this calculation. Ji Manohar.
And so the perturbation Hamiltonian will itself be an integral.
Yeah, so this is an integral. This is an inner product. It has to be found through integral. So what I need to do, I need to find this. So what I need to do is Q over 4 pi epsilon naught. Okay. Now this thing is negative. I have a single electron. So when this negative charge interacts with an electron, it produces an energy proportional to E into Q. That single electron is coming from the d orbital, integral over all of volume. Now this thing corresponds to a wave function which I've written over there, psi d1, d2, d3, right? Complex conjugate, function of r, theta and phi. It has a radial part and an spherical part. And I need to find out this thing. I will call all of this some V, some potential V. Okay? It is a function of r, theta and phi. Because x, y and z are functions of r, theta and phi. So I put a V here, function of r, theta and phi. And then I need to put this thing in here. So I put in psi, r, theta, phi. So I need to calculate this integral.
So but didn't we like the Hamiltonian initially as an integral itself in the first board, where it is being multiplied with charge density? Or is it this?
It's the same thing.
It's the same.
It's the same thing.
Because that is the charge density.
Right. So that's the total energy of the system. Okay, so this is something we need to calculate. This is in full spirit of the perturbation theory. This is the perturbative Hamiltonian, and these are the corrections to the energy, and we're lucky that we have found out the eigenstates, so we can easily compute these inner products. Now let's do this. Let's write a computer program that actually does this. Let's do it step by step. Alright, first of all I define a potential. Now this potential is 1 over square root times what I've written over here. I've defined this. exactly the same as what I've written on the blackboard. This defines a potential. Now what I would like to do, I would like to express this as a series. So as a series which has terms in x, x square, y square, z square, x square, y square, z square, right? I would like to expand this as a series. What I do a series, like to expand phi p, and I would like to return a certain number of terms. From x goes from 0 to 6, y goes from 0 to 6, and z goes from 0 to 6. And I would also like to I call this S1, and I would like to also tell my software that, okay, that's fine, that D is positive. D is positive. That's going to take some time because converting this into a series is not easy. Okay, sorry, we'll simplify. So what you see here, you get Z4 term, Z6 term, and terms of the order of Z7, etc., etc., etc. But this is not the form that we like this to be in, because Y4 is being multiplied by Z4. So what I want to do, I would like to separate out terms x square, y square, z square, x square, y square separately, x square, z square separately, etc. So in order to do this, I perform a trick in Mathematica. What I do is I define a function h which takes two arguments, and if alpha is less than beta, then this function is 1, otherwise it's 0. So I just define this. This is just a mathematical trick, nothing to worry about. So now what I do is I want to find out the coefficients of S1. Suppose I write x square plus x square into y plus x into y square, and I find the coefficient in this expression of x square, I get y. The coefficient of x square in this expression is y. Okay? If I find the coefficient of x, it turns out to be y square. So coefficient is a function that picks out coefficients. Now what I've done over here is I pick out coefficients from S1, which is the series that I developed, but I multiply the series with x, y, z. This is just a trick. I multiply the series with x, y, z, and I pick out coefficients of S1 into x, y, z. Okay, so there is an x, y, z in every term. Otherwise, there will be terms like x squared, which don't have a y or z, and I would like terms to be presented in a certain way. So I multiply the series with x, y, z, and I would like to find out the coefficient in this series of x raised to power p plus 1, y raised to power q plus 1, z raised to power r plus 1, and I would like the sum of these coefficients to be less than 4. Okay, so I want terms like x square, y square, z square, x raised to power 4, but I don't want terms like x square, y square, z square, because here the sum of the coefficient is 6. I would like to truncate at a certain point. Therefore, I multiply this function with h, and then I would like to sum up over all of these terms. So let's see what this thing does. So it's going to take some time to run this probably. It's running S2. Let's see what my S2 looks like. Now this is my S2. Nice simple form. It has separated out terms of x5, x square, y4, x square, z square. So it has simplified and truncated my series to the terms that I desire. These are just mathematical tricks that I play. Okay? Now this is my potential. This is my V. The first term is immaterial. It does not have an x, y or z dependence. So it just gives a reference to the potential and it does not contribute to the energies. So I can leave this term. So what I do, I define this to be my V. Okay. Now what I would like to do, I define my V equals this thing over here. This is my V. Okay. Let's also write down this V on the blackboard. Seven over d5, 7 over 2d5 x square, x is power 4 plus y raised to power 4 plus z raised to power 4 minus 3 x square y square plus x square z square plus y square z square. This is my potential. This is what's going to go in here. Okay, so now I need to decide what goes into the wave functions. And of course, x is equal to r cosine theta cosine phi, y equals r cosine theta r sine phi, z equals r cosine theta, x equals r sine theta cosine phi, y equals r sine theta sine phi, and z equals r cosine theta. So you have to convert to polar coordinates if you would like to stick to polar coordinates. So this is now my potential. First of all, notice it's symmetric because the environment is totally symmetric. It's a cubic environment, cubic symmetry, it's totally symmetric. So it doesn't have terms like x, y and z. It has all even square, even powers. So this is one nice thing. All of these terms are on equal footing, all of these terms are on equal footing because of the symmetry of the environment. Now we would like to define our wave functions. d1, d2, d3, d4, d5 and so on. Okay, let's do that now. Over there. First of all, I define my radial function. The radial function is picked up from the handout that I've given you. It's R32. Here it is. It's exactly similar to R32, which is in table 13.2, 8 over 81, square root 1 over 20 pi, 1 over 20, there's no pi here, pi, a cube r over a naught now is the Bohr radius, square into exponent minus. This is my r. Okay, this is the radial part of the wave function for the 3D orbital. Now each one of these is being multiplied by a spherical harmonic by the functions that I've written over there. Now my d1 equals r32, the radial part, multiplied with a spherical harmonic with L equals 2, n equals 0. Spherical harmonic y. Now my L equals 2, my n equals 0, n is 0, and my variables are theta and phi. Okay, so this is my d1. Now I need to find d2. So what I do is copy this. My d2 is defined as r32 divided by square root of 2 into the sum of two kinds of spherical harmonics. One has an m of 2, the other has an m of minus 2. I can simplify this a little bit for your convenient viewing. And simplify this further. Okay, this is a real function. It's going to be an eigenstate of the Hamiltonian. If you put this inside the integral, you make the potential act on this function, you get the same function back again. Okay, so this I've defined D2. I defined the second orbital. Now I can define D3. All of these are d orbitals. My D3 is defined as, now I take the negative of this, not yes, R32. So I multiply this with minus iota. Let's simplify this. Okay, so now I get real function D3, the third d orbital, an eigenstate of the crystal field Hamiltonian. Okay, now let's do D4. D4 is thing with the plus iota, spherical harmonic 2, 1, 1 plus right, I get D4. Likewise, I can get D5. D5. Alright, so this is also real. So I have generated all 5 orbitals, the wave functions, which are depend upon r, theta and phi. Now I would like to put these into the calculation of the expectation values, which are just the corrections, the first order corrections to the energy. So I also need to calculate the complex conjugates of these functions. Right? So I need to do that. So I need to define the complex conjugate. D1C is conjugate of D1. But the problem is that Mathematica doesn't know whether R, theta and phi are real or not. So I would like to simplify this a little bit. I would like to tell Mathematica that these are real numbers. R is real, theta is real, and phi. All of them are reals. Let's see if Mathematica can, okay. And A is also real. Is more radius. Okay, so it's stuck with this now. Let's see if I can put this. Alright. So I've defined the conjugate, the complex conjugate of one of the wave functions. Okay. So when you do mathematical programming in a software like Mathematica, you'll have to tell it precisely that which variable is real and which one is. Now I can do this for all the wave functions. Okay. I'm defining the complex conjugates.
So weren't the real functions in the first place? So the complex conjugates will be the same.
Yeah. So let's check that. D5C Is this equal to d5? Yes. Okay, so this is true for all of them. Good. This formalism will also work if you don't construct real functions. So anyway, so now what we have, we've defined all the, now let's find out the corrections to the energies. E1 is, now I have to form this integral over there. I forget about the coefficient EQ over 4 pi epsilon naught. So I'm expressing the energy in units of EQ over 4 pi epsilon naught. So I'm forgetting this thing for the time being, and I'm forgetting this thing for the time being. Okay, so I'm forgetting these on Mathematica. I don't want to plug these into Mathematica. I'll put them in later at the end. So now my E1 is, I need to integrate. What do I need to integrate? I need to integrate over all of volume, which means I need to integrate with this metric r square sine theta. First of all, I need to write x in terms of theta. I need to convert this into polar coordinates. Now I need to integrate with this metric, because I'm integrating over volume. R square sine theta is the volume metric for integration over volume, into d1 conjugate with just d1. So I multiply this with d1 and another d1, okay, and I need to multiply this with v. I've defined my v. This is my potential. Let's call this is my V, right, which I put in here. If I write V now, this is my V over here, because I put this into polar coordinates. So I multiply this with V. This is just an expression of the integral over there. I have the wave function, its complex conjugate, the wave V, and the wave function, and since all of these are position variables, they mutually commute. Now I need to define the limits of integration. Theta goes from 0 to pi, phi goes from 0 to 2 pi, and r goes from 0 to infinity. Okay, I get this value. This is the correction to the energy in the presence of the crystal field if that single electron happens to lie in the orbital which we call d1, which is dz square. Now let's find the corrections to all 5 of these orbitals. Just out of curiosity, you might like to find out what happens if I put d1 here and do d2 here. This is 0, because d1 is an eigenstate of V, and d1 and d2 are mutually orthogonal. Okay, so you can also prove that all 5 of these orbitals are mutually orthogonal. And you also need to normalize, which means you need to divide each one of these energies by this thing, by the normalization factor. If you're lucky, this is 1, because what's in your table, there are coefficients with each wave function which normalize the wave function. So in the table that I provided, you provided with normalized wave function. So everything is normalized. You have to take that into account as well.
So the range of functions in the simple harmonics we're using, they're already normalized, which is why this is coming.
What's given in your table is normalized. Some authors would give you tables in which these are not normalized. Okay? So normalization is always tricky. You just need to do proper bookkeeping to see if things are properly normalized. Now we would like to find the corrections to all 5 orbitals in energy. So this is E2. I simply replace D1 by D2. I get an energy that's similar. That's good because the d orbitals were originally degenerate. Now let's look at d3. I get a different energy this time. D3 orbital has a different energy than D1 and D. Previously, all 5 of these orbitals had the same energy.
So there's also minus sign.
Yeah, minus sign, right? Good. The expectation value of energy can be minus, the correction can be negative. For D3, D4 and D5, all 3 energies are the same. So this cluster of 5 states, 5 degenerate states, is now split up into 2 clusters, just like exchange interaction. By the way, I would also like you to see how these orbitals look like. If I plot spherical 3D, I should really plot the probability densities. So I plot B1 into D1. Right? Over some. Okay, I don't want to plot all of D1 because they have R components as well. I just plot the spherical harmonics, okay? I don't want to plot the R component, that's going to be a big mess. Harmonic. Let's plot dz square. Theta phi square multiplied with itself, right? Where theta goes from 0 to pi and phi goes from 0 to 2 pi. This is just this plot of the spherical harmonic, the angular part of the wave function. Plot spherical plot, sorry. Spherical plot. Okay, this is the dz square orbital, the probability density of it. Okay. Likewise, I can plot with an under root 2 factor as well, but don't care about this for the time being. But this okay, so this has a iota as well, or oh, this is 2 plus minus 2 spherical harmonic pi theta pi. So this is the d x square minus y square. Good. This is the d x square minus y square. Likewise, I can plot this. Just I'm worrying a little bit about the complex conjugates. Okay, so this is another thing. This is another one of them. Okay. Likewise, I can plot all of these d orbitals. So now I have 5 different kinds of energies. D1 and D2 have these energies which are the same, and D3, D4 and D5 have different energies. Now each one of these is being multiplied with an E into Q. Q is negative, E is positive with minus sign. So minus EQ is a positive number. So D1 and D2 have higher energies and D3, D4 and D5 have lower energies. So let's find out how these energy levels are split in the presence of the orthorhombic, cubic, symmetric field. And then we'll take a 5-minute break. So initially, the atomic orbitals for a d1 electron, all 5 states were degenerate. Now d1 and d2 are raised in energy. Which means that these states are dz square and dx square minus y square. Okay? And we have 3 states which are lowered in energy. And they remain degenerate. So degeneracy has been lifted by virtue of the crystal field. So these 3 states are the dxy, dxz and the dyz states. Now if you find out the amount of splitting, okay, so this is a constant, okay, so this is just going to normalize. If you just find out how much this is split and how much this is lifted, how much this is lowered and how much this is lowered, then you will find out the following. This is increased by 25515. So if this gap is, say, delta, then the amount by this is raised is 25515 over 25515 plus 17010 delta. Let's find out what this fraction is. This fraction is 25515 divided by 25515 plus 17010, 3 over 5. This is raised by 3 over 5. Now if this total gap is delta, okay, so I put this sign, this is conventional, then this raising of energy is 3 by 5 of delta, and this lowering of energy is going to be 2 by 5 of delta. But there are 3 levels here and 2 levels here. So the center of gravity of this multiplet remains the same. This is exactly similar to what you saw when you had an exchange interaction in which there were 3 kinds of triplets, 1 kind of singlet. The triplet was raised by 1 unit, whereas the singlet was lowered or raised by 3 units. So the center of gravity of this multiplet does not change. And you can actually calculate this delta. This delta is just going to be the difference of these energies. Okay, so the delta for an orthogonal or a d1 ion placed inside an orthogonal environment is going to be, there's an A04 over d5, then there is EQ over 4 pi epsilon naught, then there is a 7
This includes a 7 over 2.
It includes a 7 over 2 in 8 minutes. A04 over d5. There's a 7 over 2 d5. There's this term over here. Why is this A04 over d5?
So क्योंकि सर हमने जो वहाँ पर मैथमेटिकल में b डिफाइन किया था हमने उसमें फॉरगेट नहीं किया था 7 over 2 d5 को. That is included.
Oh, so okay. Okay, that's already included. Okay, yes, you're right. So this is already included, and you have 25515 minus of this, which is this 17010. This is the octahedral splitting. Okay, it's a function of the Bohr radius, it's a function of the distance. Smaller this distance, bigger will be the splitting, which means higher the interaction. Now if you want to look at this graphically, what's happening is you have dz square orbital which is increasing its energy, and you have the dxy, x square minus y square, that is increasing its energy, and this makes intuitive sense as well because the electron is placed here on this axis. In the dz square orbital, the electronic density makes overlap with this anionic charge and the energy of the system is raised. So these orbitals overlap with the ions and both of them are negatively charged, so the energy of the system is raised. Likewise, for this system, the ions are placed here. So this raises the energy of the system. For the other three kinds of orbitals, for example, for the dxy orbital, the anions are placed here, but the wave function, the probability density, avoids the electrons. So the energy of this configuration is lower than this configuration. So everything is making physical sense as well. Hence, what we have here is due to the crystal field, the degeneracy in the d orbital is lifted. Now you have one electron. If you have one electron, that of course goes into the lower energy state, into one of these orbitals. We'll also see after a 5-minute break what's going to happen if we have more electrons and what happens if the environment is tetrahedral. Alright, so let's take a 5-minute break. Let's reconvene in 5 minutes.